Hello, we are Team What the Fish. Our host today will be Fuyen, Claudie, Dewang, and me, Hersey. And the topic we're going to talk about today is Scala. So, what is Scala? Scala stands for Scalable Language. It incorporates with both object-oriented and functional programming into extremely concise. Scala is not only an attempt to become a better Java, but remain very close in syntax to Java language itself to reduce learning curve about 50% code reduction in overall. Since it's built to replace Java, it can implement most of the existing Java library out there. And let me show you an example. We are going to simulate the process of slicing fruit. First, we have an apple. In Java, we usually create an object first. In this case, we create an apple object. Then we create a method to dice it. But what if we have to dice a pear too? The goal might still be easy. You create a fruit object with abstract dice method, and both apple and pear class extend the fruit object so that we can use the abstract dice method to dice it. But what if there are more and more objects coming in and we only have one dice method? Scala solves this problem. Scala is both object-oriented and functional programming. You can still create the object like apple, pear, or watermelon. And we can build a dice method which represents as a knife here, which takes in any object and dice them. Since the function does not have any locks, we can perform them simultaneously with different objects. 卖兔料, let's talk about Scala concurrency. But today we are only focusing on actor model and software transactional memory. Let's talk more about Scala concurrency.
So one interesting aspect of Scala that makes concurrency easier is something called software transactional memory, or STM in short. So STM serves as an alternative to combat race conditions without having to delve into the troublesome locks and threading itself. So, just a quick recap of what race conditions are. A race condition happens when two instances or threads access shared data, and in turn, this creates unexpected results where the order is dependent on the thread's scheduling algorithm. A simple example here shows a method called measure, which increases the measure count, which is of type int. So in a typical program, even a method as simple as the one illustrated here, measurer, is susceptible to race conditions. For example, take a look at measurer here. It increases measure count each time it's run. So what happens if two threads or two workers run the same measure method? It will produce a race condition where the measure count will not be the same itself. So this can lead to unexpected results. So a simple way that we have learned to combat this is to implement a simple lock. So this way we ensure that no two threads access the same shared data. As you can see in the example, we just do a lock and then we unlock once we finish editing. However, locks are not that simple now, are they? For more complex programs, locks can easily lead to deadlocks. And like the lab test, locks can be a little complex to implement in order to achieve the maximum concurrency and parallelism. In addition, worker threads that are trying to access the shared data will have to wait for the locks to be unlocked or the shared data to be released in order to proceed. This utilizes a pessimistic approach. So a nice way in Scala to combat this is to use software transactional memory, or STM. So what is software transactional memory? So STM is actually a concurrency mechanism similar to that of a database, which makes use of transactions for controlling access to shared data or data pool. So two key features of STM is the use of optimistic approach or optimism and the use of transactions. So in STM, an optimistic approach is used. So methods accessing shared data assumes that there are no errors, unlike in locks, and proceeds to continue its assigned task and access the said shared resources. Only once the task is completed, it will then check if there are any errors or conflicts. If a problem or conflict occurs, it will clean up and or rerun the tasks. This ensures that no worker threads sit idly while waiting for shared resources to be released. So as you can see, a typical pattern is as such, where the thread proceeds to perform a task and a check-in or save, and if it sees that an error is present, it can roll back the changes and rerun the method using the updated shared resource values. This way, it prevents race conditions from happening. So the other key feature of STM is their use of transactions, which takes a similar fashion to that of a database, where changes are committed in a transaction. Essentially, it records all the transactional variables in what we call a transaction block. And in turn, this becomes an atomic block, where either the whole collection of changes is updated at once to the shared data pool, or the whole update fails. This guarantees there's no instance where only half the changes in an update is written while the other half fails. So, utilizing these two key features, Scala performs STM in such a manner. Let's say I have a method called measure, which alters the measure count again. So STM creates a transactional block each time an actor calls this method and copies the value to be updated. So for instance, if actor A runs measure, it will have its own transactional block. In turn, if actor B runs measure, it too has its own transactional block. Let's say if A and B both run measure at the same time. So when A runs it, measure count is updated and committed as the new value. At the same time, when B tries to commit the value, it detects that there's a change in measure count and rolls back the change. At the same time, B detects a change in measure count and rolls back the changes. It then retrieves the new measure count and reruns the method. So software transactional memory provides an alternative to the use of locks like what we have learned in Java. So in order to utilize it in Scala, it's even easier. We just have to define our variables with the ref type, ref, which wraps our variable. And then in the method itself, we just have to specify it in an atomic block and wrap the method in the atomic block, and this in turn tells Scala in the software level to actually run STM.
Now, let's talk about the actor model. The actor programming model is aimed at avoiding all the problems we mentioned before. Unlike the widely used approach of shared multiple states, it requires you to design and write your application from scratch with concurrency in mind. The idea is that your application consists lots of entities called actors. The actor is an object which encapsulates state and behavior. Each of these actors is responsible for only a very small task, and they cannot live on their own. Each and every actor is created by an actor system. Based on your use case, your application may consist of a few dozen or few million actors. There is not a one-to-one relationship between an actor and a thread. One thread can execute many actors, switching between them depending on which of them has messages to be processed. It is important to keep in mind that sending a message and processing it is done in an asynchronous and non-blocking fashion. The sender will not be blocked until the message has been processed by receiver. Instead, they can immediately continue with their own work. Maybe they expect to get a message from your actor in return after a while, or maybe they are not interested in hearing back from your actor at all. What really happens when someone sends a message to your actor is that this message is delivered to the actor's mailbox, which is basically a queue. Placing a message in an actor's mailbox is a non-blocking operation. The sender doesn't have to wait until the message is actually enqueued in the recipient's mailbox. The dispatcher will notice the arrival of a new message in an actor's mailbox. If the actor is not already processing a previous message, it is now allocated to one of the threads available in the execution context. Once the actor is done processing any previous message, the dispatcher sends it the next message from its mailbox for processing. In Scala, there is a hierarchical structure for actors. One actor which oversees a certain functions in the program wants to split the task into smaller, more manageable pieces. For this purpose, it starts child actor and supervises it. And if one actor cannot deal with the situation, it sends a corresponding message to its supervisor asking for help, thus enabling a system to recover from failure. An important part of actors' fault tolerance actually comes with its ability for a parent to manage the life of child actors.
Now you have an overview of how the actor system works. We have prepared a simple program to demonstrate how this concept is used to help with concurrency.
From this demo, we will be using Scala actor system to simulate a coffee shop operation. Here we create an actor called Barista. She is the employee of our Scala coffee shop. She can do a few things. She can take in order, two types of order, cappuccino request and espresso request. She can also send the bill to whoever orders the drink, and she will prepare the drink by printing a message. Let's prepare a cappuccino or let's prepare espresso. Next, we will create another actor called the customer. The customer takes in another customer reference as its parameter, which is called caffeine source. When we declare the customer, we'll assign barista to the customer's caffeine source. In this way, customer can only order drinks from barista. From object sales, we will simulate a coffee shop sales. Here, customer creates an espresso order. This order is sent to caffeine source, which is barista. Barista takes in this espresso request. She does two things. She sends out the bill and she prepares the drink by printing a message, "Let's prepare an espresso." Once customer receives the bill, customer will print another line, "I have to pay 200 cents" to simulate the process of customer making the payment. Now let's run the program. As you can see here, barista prepares the drink before customer make payment. We will run this program multiple times to get a different result. As you can see here, the order has changed. The customer make payment before barista prepares the drink. The reason why we are getting a different output, as DeWong has mentioned earlier, actors in Scala sends message and process it in an asynchronous fashion. The sender, in this case, barista, she sends the bill to customer. She does not wait for the customer to make payment before she prepares the drink. This explains why the output shows that she prepares the coffee concurrently as the customer is preparing to pay the bill. Here comes to the end of our presentation on Scala programming language. Thank you.